Welcome everyone to this new seminar of NAG ROMS series. Today with us we have Professor Simona Perotto, and she will talk about hierarchical model reduction, background, applications, recent progress, and future direction. So please, Simona, the floor is yours.
Thanks a lot. Thanks, Maria, for the introduction. Thanks to all of you for the kind invitation. It's a pleasure for me to attend this seminar series. Today I will speak about a model reduction technique that it is on the table from some here. So we speak about hierarchical model reduction, and my goal is to provide you the background of this approach and contemporary to show you some possible applications of this method along with recent progress and future direction. So hierarchical model reduction, or in a short way, HiMod, is the ideal tool to model which are characterized by a strong directionality. Here you have examples from different fields of application. For instance, you can think about a flow inside a pipe, or an acoustic wave traveling along a waveguide, or you may have a water flowing inside an aquifer, or the blood flowing inside an artery district, for instance. But the additional information is that beside these dominant dynamics, you have also a local dynamic which may be meaningful only in specific portions of the domain. In the first example, for instance, you may have a valve which induces a transverse dynamics in this position. The waveguide, for instance, may be characterized by an irregular shape, and also this irregular geometry may induce some transverse phenomena of interest. Concerning the aquifer, you may have a well which moves the water upward and thus induces a transverse phenomenon. And concerning the hemodynamic setting, which is, by the way, the first setting we started from in the development of this new approach, you may have, for instance, the deployment of a stent which induces a transverse irregular dynamics, or the presence of another disease very well known, for instance, an aneurysm, with which is associated with the presence of transverse blood flows. So the idea we exploited some years ago in the setting of this new model reduction approach has been essentially to exploit the co-presence of these two different dynamics characterized by two different weights. So we decided to discretize the mainstream by resorting to, for instance, a standard finite element discretization, a 1D approximation, while describing the transverse and, I would say, secondary dynamics by resorting to, for instance, a standard Fourier expansion. So we deal with a basis of modal functions, so that at the end of the day, your reduced model, your reduced space does coincide with the following collection of linear combinations of finite element function associated with the x direction, and whose coefficients coincide with the modal basis function, which may be, for instance, sinusoidal function. We will comment on also on this choice. And actually, we are in the presence of a hierarchy of reduced models where the different level of details is set by the choice done for the modal index M here. I mean, from the number of modal functions that we decide to adopt to describe the transverse dynamics. And the idea might be, for instance, to properly tune the number of this modal information in order to match the less or more complex transverse dynamics For instance, coming back to the example from hemodynamic, the idea might be to resort to a small number M of modes sufficiently far from the aneurysm, while resorting to a larger number of modal basis function in correspondence of the aneurysm itself. Of course, there are ideas similar in the literature, similar but not the same in the literature before our contributions, and at the same time other works have been developed. This is not an exhaustive list of contributions. I mean that you can find contributions in such a direction also, of course, our first papers. And another feature, important feature of the high mode approach is, this is rather standard, I would say, in several contexts of scientific computing, is the fact that we play with map which have to be characterized by a certain regularity. I will come back to this topic later in the next, in the last part of the presentation. So it is used to resort to suitable maps that change, for instance, the shape of your transverse section into a shape of reference for your fiber. So for instance, a circle, okay, in the 2D case. And the definition of these pointwise map psi-eggs induces the definition of a global map between the whole computational domain omega and what we call omega hat, which is a reference domain, which is a very easy context where computations are easy to be carried out, and the idea is to perform many of the computations you need only once in this reference context, and then play with a suitable map to move this computation into the physical domain. So these are the main ingredients to state the high mode formulation. The high mode reduction, the high mode approximation applies essentially to the weak form of your full problem that is here formalized in the standard search of a function U belonging to a space V, such that the following equality is satisfied for each test function V in the space capital V. And at that point, the high mode problem simply reads in the same way. The idea is the one typical of a Galerkin approximation, where essentially you work in a smaller space and your smaller space is represented by the high mode space. And if you exploit in this formulation the modal representation for your high mode solution UMH, and you adopt a similar representation for the test for the high mode test function VMH, what you get at the end of the day is the possibility to rewrite your full problem into a collection, into a system of coupled 1D problems. And this is interesting. Especially if your full model is a 3D model, in the sense that you can commute a problem formulated in a three-dimensional environment into a collection of problems which are, of course, coupled. But they are defined, they are associated with the mainstream, which means with the one-dimensional domain. And this unavoidably leads to a collection of advantages. For instance, just think about the need to discretize your domain. So you can replace, in such a case, the discretization of your, for instance, patient-specific artery with the tessellation of a one-dimensional entity. And of course, which considerably simplifies the computational effort. Thanks to the introduction of the map, you are led to solve your problem in the reference domain, so a friendly environment. And it can be proved that if your modal index is sufficiently small, at that point, the high mode approximation is expected to be convenient from a computational viewpoint when compared with the approximation of a full problem. Just to make easy computations, if, for instance, you assume to solve your finite element, your full problem on a cube, on a d-dimensional simplex, and you adopt nh degrees of freedom along each dimension. This means that the number of degrees of freedom associated with the full approximation is equal to nh power d, while we keep the same number of degrees of freedom along the mainstream for the high mode. So you have nh, but nh power d minus 1 is replaced in the high mode representation by the modal index m. And this means that if m is smaller compared with nh, actually the number, we will see this in some computational, some numerical examples, the number of degrees of freedom required by a high mode discretization is expected to be lower compared with the number of degrees of freedom associated with a full discretization. And finally, from an algebraic viewpoint, what you discover is that you may a priori exploit a particular sparsity pattern characterizing your high mode discretization, in the sense that what you get from an algebraic viewpoint is a block-wise matrix. In particular, each block exhibits the sparsity pattern characterizing the discretization you select along the main direction. And for instance, in such a case, this is the matrix associated with a high mode approximation characterized by free modes along the transverse direction, while you have 14 degrees of freedom concerning the approximation of the mainstream. And the approximation is in a finite element discretization. Indeed, you recognize the standard three-diagonal sparsity pattern characterizing such one-dimensional discretization. We have worked a little bit on this algebraic structure, but there is a lot of work to do still in such a direction. So I have to say that currently we have not been so good to exploit in a constructive way the algebraic high mode structure. Okay, this is a simple example just to qualitatively verify that high mode actually works. So we are solving inside a parallelepiped an advection diffusion problem characterized by two localized sources inside the box. And then you have a horizontal wind. So what you get is represented by this solution. Here you have a free longitudinal sections of the solution. And then you have a comparison with the high mode approximation when you gradually increase the number m of modal basis function. Below you have a zoom in correspondence with the middle section, and we can recognize that the high mode approximation on the right becomes closer and closer to the full solution as we gradually increase the number of modes. For instance, for m equal to 25, the correspondence between full and reduced solution is very good. Okay, now I have tried to enucleate some of the main issues characterizing such a reduced modeling. So the first issue is the selection of the modal index m. Concerning this problem, we can, for instance, we can carry out an a priori choice, I would say also a heuristic choice, such as the one characterizing these examples. So what we have done here has been simply to gradually increase the number of modes until we recognize a good matching, a good qualitative matching between the full solution and the reduced one. This is a possibility. Or on the other end, you can do something which is more mathematically sound, I would say. So this means that you can carry out an a posteriori modeling error analysis. So there are essentially two main works on such a direction. The first one is related to a steady configuration, while the second paper, the most interesting one, is related to an unsteady configuration. And the final goal is to have a mathematical tool, which is the a posteriori modeling error estimator, which allows you to choose in an automatic way, to select in an automatic way, not only the number of modes to be employed for your high mode approximation, but for instance, also the discretization along the supportive fiber, if we think about a steady configuration, or for instance, also the time step, if we consider an unsteady setting. So in both cases, we have developed such an analysis in a goal-oriented setting, where essentially the goal, the idea is to limit, is to control, is to build a control of the goal error. So the difference between the value of a goal function, which mathematically translates a quantity of interest, and the corresponding quantity evaluated on the high mode solution. And this goal error is controlled in terms of our modeling error estimator, which has been derived under a rather, I would say, recurrent assumption in a context such as this one, where you have a hierarchy of richer and richer reduced models. And essentially, this saturation assumption demands that the reduced approximation provided associated with a larger number M plus of modes is in general provide us with a better approximation with respect to the discretization provided by the high mode approximation for M, where M is strictly less than M plus. So if you have at your disposal these two reduced high mode approximations, you can define your error in such a way. And at this point, you have your automatic tool to select the number of modes along your domain. But if you, since you have not only to select the number of transverse modes, but also to identify, for instance, the finite element discretization of your mainstream, what you can do is to combine the control of the modeling error with the control of the discretization error by properly adjusting the standard goal-oriented analysis, for instance, for finite elements. And this is exactly what we have done in both of these contributions. And here there is what I have done together with Alessandro Ziglio in 2015, so a lot of years ago, to control not only the time step, but also, to control not only the space step, but also the time step. So it is rather standard in such a context to define the a posteriori error estimator for the discretization error, which is a space-time discretization error, in terms of two contributions, eta SH, which is the error estimator for the space, and eta TH, which is the error estimator to control the time. And the strategy in both of the cases is to properly rewrite what is known as residual rho and what is known as weight, in terms of, I would say, by highlighting the contribution of the space step, if we think about the spatial error estimator, or the time step, if we focus on the time contribution. And the possibility to highlight these two informators is crucial in order to predict the partition of the mainstream as well as the subdivision of the time windows you are interested in. So the other terms seem ugly, but they are absolutely beautiful. Essentially, they do coincide with the residual associated with the internal part or with the boundary contribution. So J very likely is a jump across the different space subintervals, plus some projection error, plus some error on the initial quantity. And what you get at the end of the day is a fully automatic prediction to identify your reduced model in terms of modal basis function, I mean number of modal basis function, and the space-time partition. We called such if you want, the collection of all these information lookup diagram, and in a few seconds I will show you an example of a lookup diagram associated with this specific test case. So on the left, you have a full solution. Now I describe what we are simulating. On the right, you have the corresponding high mode approximation. So essentially, we are solving again an abduction diffusion problem. We have a localized source term here, and then we have a horizontal wind. And when times goes on, what you get is that this wake is developing and slowly it reaches the right boundary of the domain, okay? So what we want to control, remember that we are working in a goal-oriented setting, is the mean value of the solution, so essentially the solution at the final time. So on the right, you have what the high mode approximation provides us. So this is the high mode solution at the beginning, and we can recognize that the reduced approximation is very far from the full solution, but we also recognize that the high mode discretization becomes closer and closer when we approach the final time, which is exactly the time when we are interested in controlling our solution. So essentially, this test case tells us that since we are interested not in controlling the norm of the solution for the whole time window, but we are interested in monitoring the solution, the mean value of the solution only at the final time, it is important that the reduced solution becomes closer to the full solution only during the last part of the time window. And this is the reason why during the first times the high mode approximation is very far. Very likely here we will employ very few modes because we are describing something which is definitely simpler with respect to the full approximation. And here we have an example of what we call lookup diagram. So the gray map essentially is associated with the number of modes. So white means few modes, gray a larger number, black the highest number of modes. While you have along the horizontal axis, you recognize the space partition. Along the vertical axis, you recognize the time subdivision. So what we recognize is that the number of modes is for all the time window very small, and such a number gradually increases as far as we approach the final time. Indeed, we recognize white, light gray, and black in correspondence essentially of the source location, which is 1.5. At that point, we recognize that the spatial grid is always refined in correspondence of the source term, and as far as we approach the final time, this the spatial mesh refinement increases also in correspondence with the wake of the solution. And concerning the time window at the beginning, the time step is kept as very small, but gradually the selection for this value is relaxed, and only in correspondence with the final time, again, we have a refinement of the time step. Keep in mind that the free information modes, space and time are interacting each other, so it is not always so linear what is exactly going on, but the message should be, I mean, in my mind is rather clear. So at the beginning, everything may be very coarse, but while we approach the final destination, at that point, every contribution mode, space mesh, spatial mesh, and time mesh are properly refined. And this prediction has been carried out, of course, in an automatic way, thanks to the employment of a posteriori error estimators. A second issue is the discretization that we decided to switch on along the mainstream. So as I have already anticipated, the original choice has been to resort to a finite element discretization along the mainstream. This is the first choice historically done, but then we very quickly understood that if we are interested in managing curvilinear center lines, such as, for instance, the ones typical of a patient-specific geometry, at that point, a finite element discretization may be very likely not the best solution. So we decided to, in some sense, exploit the high geometric efficiency and flexibility of isogeometric analysis. And so what we decided to do has been to replace the head functions along the mainstream with the standard B-splines, thus giving rise to a smart combination of I-mode with IGA. And so we obtained what we have denoted by Higa mode. And here we have first check on a benchmark configuration. So we have a wavy channel whose amplitude is diminishing. We are approximating via Higa mode the Stokes problem. In particular, on the right column, you have the pressure. On the left column, you have the modulus of the velocity. The first row is associated with the reference solution. So a finite element approximation, P2 for the velocity, P1 for the pressure, for the standard in soup requirements. And the two next rows are associated with a high mode approximation, where we resorted to a finite element of degree 3 for the velocity and 2 for the pressure, while the number of modes is equal to 7 and 5 respectively for velocity and pressure in the second row, 17 and 15 in the third row. Why this choice? Because we recognize that, for instance, both the pressure and the velocity exhibit an irregular path where the full solution is smooth, and this justifies the increment for both the modes associated with velocity and pressure. And indeed, the high mode approximation that you have in the last row is fully comparable with the full solution. And the interesting information is the one related to the DOF. Indeed, we are able to save a lot of, in terms of degrees of freedom, just compare the number associated with the full finite element discretization and the best high mode discretization. So essentially, we gain 2 orders in both cases. The idea to switch on an isogeometric discretization of the center line has been crucial, and I would say instrumental also with the idea of moving towards to move from benchmark context to real world approximation. In particular, I'm referring to specific patient geometries. Indeed, we have settled an approach to parameterize the domain, the computational domain, so a swept volume approach based on NURBS. So the idea is to recover the volume by moving through the space a two-dimensional shape whose geometry may change during the sweep. So we have described this volume, this parametric volume, by resorting to a parametric representation based on the so-called control points, which are collected in the vector D, and the rational splines, which are represented by this function here. And the idea is to identify the Nurse volume via a variational approach. I mean that we minimize an objective functional denoted by L, which combines essentially a standard mismatch contribution with geometric constraints on the, we are essentially controlling the orthogonality of a transverse section with respect to the center line. We have a rotation constraint so that no torsion around the center line is in theory allowed. We have a constraint on the regularity in order to avoid possible oscillatory trends of the whole geometry. And finally, we have a constraint on the shape to minimize shape variation across the sweeping process. And here we have a first simulation. So we deal with the blood flow modeling in a cerebrovascular arterial branch. So the geometry is not too complex. So this is just a warm-up test case. On the left column, you have the finite element approximation, so the full model. On the right column, you have the Higa mode discretization. The pressure is above, the velocity is below, so we can recognize a good agreement from a qualitative viewpoint between full and reduced approximation, and also the error for both pressure and velocity with respect to both VL2 and the H1 semi-norm, is not so bad. But the additional good news is that the time is essentially divided by 4, then we resort to the high mode approximation. And this is a more challenging configuration. So we are dealing with a stenotic lesion in a coronary artery. You see that the geometry here of the patient, the configuration of the patient is very compromised. So again, we compare a 3D full finite element P2, P1 approximation by solving the Stokes equation with the Higa mode approximation for these choices of finite elements and for this number of modes. And the interesting information is that also for this more complex case, beside the good matching from a qualitative viewpoint for both pressure and velocity, the good news is that the possibility to considerably reduce the computational time. And we have exploited this test case also to carry out, I would say, more clinical investigation, in the sense that we have exploited the reduced context to compute one of the medical index which are currently used by doctor in clinical application, the so-called fractional flow reserve, which is essentially a measure of the pressure after and before the stenosis. So in green, you have the trend of the FFR along the center line, while in cyan, you have the same prediction carried out by means of the Higa mode approximation. And it is interesting to realize that both the approximation essentially identify the same location where this strong drop takes place. And both of the approximation essentially identify these trend as a high risk profile. So this is, if you want, an additional information that may have an impact if you decide to resort to the reduced contribution, also from a practical viewpoint, I mean in clinical practice. Okay, as a third item, we can cite the selection not only of the discretization along the mainstream, but also of the modal basis function in order to describe the transverse dynamics. Also, in this case, we started from the simplest possible choice, I mean a sinusoidal function with a consequent limitation on the boundary condition to be applied along the horizontal boundaries. But then in a next work, we provided an approach that we named educated high mode approximation, where essentially, in order to recover the possibility of assigning any boundary condition along the horizontal side, we decided to build a so-called educated modal basis function, which means that we solve an additional problem, a Sturlingville problem, along the reference fiber, and we complete such a Sturlingville problem exactly with the boundary conditions assigned in correspondence with the horizontal sides. And this choice allows us to impose in an essential way the boundary conditions to be assigned along the desired piece of boundaries. And this means that we can resort to the eigenfunctions of a Sturlingville approximation as a modal basis function. This is the idea behind an educated modal basis approach. More recently, we have, and this for the first time represents a different field of application with respect to the standard hemodynamic context. We have applied with some colleagues at the engineering department of Politecnico di Milano, we have applied the high mode reduction for the modeling of the wave propagation in the acoustic wave propagation inside a pipeline which may exhibit a deformation. So essentially, the problem that we have solved in such a case is the standard linearized acoustic wave equation in the frequency domain. And we have selected in such a case as a modal basis function the eigenfunctions of Helmholtz equation, of course, properly closed with suitable boundary conditions. Here you have some examples of such eigenfunctions. I'm not an expert of this topic, but essentially what the colleagues have done to verify the good properties of high mode approximation has been to compare the output provided by the high mode approach with the outcome of console multiphysics for two different choices of meshes. A first one, the green line, which is coarse, and a finer one associated with the red contribution in the plot. And the configuration is essentially this pipeline. Here you have two settings characterized by two different types of deformation. So we have a restriction on the top and an enlargement on the bottom. And then you have to think about two ports associated to this device, an input port and an output port. So essentially, to evaluate the reliability of a proposed approach, we have considered the so-called scattering matrix. Indeed, this matrix models the set of all the scattered modal waves induced by all the possible incident modal waves when applied once at a time. And here you can compare, you can realize that the blue line, which is the high mode approximation, correctly mimics the trend associated with the full COMSOL approximation for the finer mesh for the first two indices, for the first two components, S11, S21, and the last one. While, okay, S31 is a little bit problematic because ideally this component should be equal to minus infinity, since the mode is not excited by the deformation. And what we recognize is that, okay, the green line is not reliable as for the other choices of the scattering matrix components, while the blue line and the green one are doing something which is not so I would say reliable, but I think also interesting from a physical viewpoint. So the good news is that the first two and the last coefficients are correctly tracked by the high mode approximation, and we are able to recover the trend provided by the full solution with a CPU time which is about 200 times smaller compared with the full approximation. So high mode is able to considerably reduce such a time. And there is also a second paper, the one after this one cited here, where we replicate the similar analysis, but in that case we solved the Maxwell equations, and the idea is also in that case to exploit the transverse electric and magnetic modes in order to describe the transverse dynamics. And also in that case, in the presence of different possible configuration for your waveguide, we have been able to correctly replicate the trend of, again, the component of the scattering matrix with a considerably lower CPU time. And finally, as last issue, there is the problem of dealing with complex geometries. Indeed, as I have anticipated, both the maps, the one associated with each point, phi x, and the global one, capital phi, between the whole physical domain and the reference domain, are subject to smoothness constraint that you can see here cited. This means that certain configurations which are recurrent, for instance, in the hemodynamic modeling, such as bifurcation, are by definition excluded by these requirements. So what we are proposing in the paper, in this paper that we are finalizing, is to, in some sense, exploit high mode where it is possible to do that, which means before the bifurcation, for instance. So pipes are tackled by resorting to high mode, while we proposed essentially to manage the bifurcation area by means of a standard finite element discretization, so a full problem, completed, we combined with a standard proper orthogonal decomposition in order to have the combination of reduced models, and then to link the two different reduced approximation. We have decided to resort to a standard domain decomposition approach. So just to sum up, pipes are tackled via high mode, the bifurcation with a standard full finite element approximation combined with a POD, and the junction via a domain decomposition algorithm. Okay, we have learned already everything about high mode. Concerning the bifurcation, the idea is to select, as usual, a standard parameter. I will come back in order to provide more details about this parameter in the next slides. And here we solve a certain number of high fidelity problems. At this point, we build such a solution for different choices of the parameter eta in the so-called response matrix. Then we define the matrix C, which is the deviation of U with respect to its mean value, as usual. At this point, we perform the singular value decomposition of matrix C. And this allows us to extract the proper orthogonal decomposition reduced basis. So we decided to keep a certain number nu r of POD modes, which are, of course, expected to be, this number is expected to be considerably lower with respect to the dimensionality of the full problem. And at this point, we select a new value for the parameter. And via a projection step, we recover the new approximation. So, and this is carried out according to a standard offline-online paradigm. Concerning the junction of the different models, essentially we resorted to a domain decomposition, in particular a Neumann-Dirichlet scheme. And the parameter, now I provide you some details about the selection of the parameter, since we have included the possible effect of the upstream and of the downstream branches of the bifurcation into this parameter. In particular, eta has been defined by, first of all, collecting some data associated with the problem, the physical problem we are dealing with. This means the two components of the three components, three in such a case, of the advective field, the diffusive and reaction contribution. Then we have added an outlet observation that replaces essentially the downstream, the presence of the downstream branches. And this means to include in the parameter the normal derivative of the solution evaluated at the nodes of the outlet boundary. And finally, we have included the inlet observation that replaces the upstream branch, the presence of the upstream branch. And this, thanks to the Neumann-Dirichlet condition, means to add the value that the solution takes in correspondence of the nodes of the inlet boundary for the second domain. And here you have some examples of the effectiveness of a proposed approach, starting from a benchmark configuration. So this is a Cartesian domain where here you have a collection of data characterizing the simulation at end. So we perform this cut. So we have 3 subdomains, and as anticipated, we resort to a mode along the branches and to the reduced formulation combined with POD in the central area, plus the domain decomposition approach. This is what has been obtained with the reduced formulation, and this is the error that we have with respect to the L2 norm. While this plot shows the trend of the relative error across the domain decomposition iterations, so it can be realized that for both the L2 and the H1 norm of the error very quickly drops and stagnates in a few iterations. This is good because, of course, the domain decomposition may be an additional source of computational effort. So one of course has to pay attention in order of not losing what you have gained with the reduced approximation when you switch on the domain decomposition step. We have replicated the same check, moving to a more realistic setting. I mean, from a Cartesian to a circular section. Again, here there is the list of data characterizing the second configuration. Again, similar cuts, and the reduced approximation, the error is very similar. And finally, a cylindrical section. This is a tentative to create a virtual bifurcation. So in such a case, we have applied this new segmentation of the geometry, and this is what the proposed approach provides us as a surrogate for the full solution, with an error, a relative error of 4.5 with respect to the L2 norm. Then just to to sum up what you may have also at your disposal in the literature, keep in mind that we have developed also a parametric counterpart of the high mode discretization. Essentially, we have settled two approaches that we call high PUD, that merge hierarchical model reduction with a proper orthogonal decomposition. You may find all the details if you want in these two papers. This is a contribution in a book, so it is a very preliminary work. This is something more rigorous and more recent. And there is already another work in collaboration with Gianluigi, a student that we co-supervised, Matteo Zancanaro. It is another way to carry out high mode in a parametric way. And here the idea is to combine high mode with a reduced basis approach in order essentially to exploit the greedy algorithm. This means in order not to compute all the solution associated with all the values of your parameters, but creating your reduced space step by step. And in this paper, there is also a comparison between the two approaches, high mode, high pod, high mode plus PUD, and high RB, high mode plus reduced basis. And I just show you the slide which sum up in some sense the result of this comparison. Essentially, what can be derived by considering a comparison of the two approaches in terms of, for instance, the cost of the offline phase, is that the high PUD approach is the best choice until the dimension of a training set is not so huge. But at a certain point, there is a point where the configuration is exactly reversed, in the sense that if such a number of training values increases too much, at that point, the high-RB approach becomes more competitive. This is essentially due to the fact that when you resort to a greedy approach, you have to include in the computational effort also the computation of the error estimator. And essentially, you can remark that the trend is almost flat for the reduced basis approach, while significantly increases when you resort to the PUD approach, where you can skip the evaluation of the error estimator, but on the contrary, you have to compute all the possible scenarios for all the choices of your parameters. So in some sense, there is this double phase configuration where, just to sum up, if the number of different scenarios is sufficiently small, it is better to resort to the high PUD approach. Otherwise, high RB seems to be the right choice. And just to provide you with some hints about what we are working on. So there are two collaborations with Ciaccone Rebollo and his group, together with Erika Temellini, who is a PhD student of mine, and Francesco Ballarin, who everybody knows here. So we are working in proving an IMSUP condition for the high mode discretization for the Stokes problem. We are starting to work on the addition of a turbulence contribution in the Navier-Stokes equation. And in the context, all this activity as a part of this presentation have been carried out in the context of project, the European project ARIA, whose principal investigator is Angelo Iollo at Bordeaux. So in collaboration with other members of the ARIA project team, we are trying to validate our approach on real cases, such as patient-specific configurations. And this is another topic we are interested in a more simple, I would say, scalar context. So try to understand how to manage the stabilization, for instance, of advection diffusion reaction, and maybe later the Stokes problem when we are dealing with a high mode approximation. Sorry for, of course, the standard delay.
Thank you. Thank you, Simona, for the very nice talk, very inspiring. So now it's question time. So if you have questions, you can unmute yourself directly and directly ask Simona your question. So maybe I can, oh, Trajan, go ahead.
All right. Okay. So very nice talk, Simona. I really enjoyed it. And so I really like, so just before the question, I really like this idea of combining things like reduced order modeling and data-driven modeling with traditional classical type of methods. I think that this is a very good idea. So then kudos for you guys, because you did this a long time ago. I think that's an excellent idea. So so the question I have for you is, maybe it's a silly question, but so if I understand correctly, so the idea would be that you look at the domain or the application that you're interested in, and if you see a preferential direction, so some sort of right, like for like blood flow, like the direction of the flow, so then of the domain, so then you know pretty much what direction you're gonna be using for finite elements and what direction you're gonna be using. Okay, so my question is, can you do similar things if you but without looking at the domain? So maybe if you have a problem or you have an internal layer or internal preferential direction. I'm thinking ocean modeling, and you have the jet stream or something like that.
Okay.
Could you do something similar?
I have only once discussed about that with a colleague who was in Nottingham and then moved in another university. And he was interested in something which sounds similar to what you have just said. He was interested in a simulation applied to the brain cortex. And also in that case, there is, of course, an intrinsic dimensionality of the phenomenon to take place. So the idea was to try to understand if actually this directionality may be not necessarily aligned with one of the standard direction. I think that your question is in such a direction, correct? Yeah, I think that it is not trivial, but maybe you can do something in that direction. Just to be honest, I have seen high mode to effectively and efficiently work also in settings where there is not a so strong directionality. But okay, the whole high mode setting has been conceived under this assumption, so this is what we sell.
I understand. That's fair enough. That's fair enough. Yes.
Yeah.
All right. Thank you.
Yeah, welcome.
Are there other questions?
Hi,
Yes.
Maria.
Yes, Thomas. Hi.
I have a question, but I don't find how to leave my hand. So, hello.
How are you?
Fine, thank you. Okay, so my question is about the speed up that is achieved with the high mode. It is, for what I have seen, is about 4 times faster than the full 3D simulation, for instance, no?
For the hemodynamic setting, yes, this is essentially the magic number that we got in that we have in all the simulation. I come back here, voila. Okay. Yeah.
So, but my question is, can this be improved if the, how to say that, the functions, the basis functions are specifically designed for the actual problem we consider?
Indeed, if you have a look to the results from the electronic department,
okay,
and I have to be honest, I understand very few of these very boring things. Anyway, in such a case where I love this topic. In any case, here the model basis function is properly customized onto the problem. No? So here they decided without any theoretical support to select as a model basis function the eigenfunction of a problem related to
Okay.
the full
I see.
model. And the gain is absolutely better than 4 times. So I do not know if console is particularly badly performing. No idea. But the mismatch is terribly higher in such a case. So probably, and this is in some sense aligned with what we have discussed about in Paris this autumn. Probably the choice of a customized model basis function may improve more and more the gain.
Okay.
Yeah.
Okay. So we have something to do.
A lot of things to do as usual.
A lot of things.
A nightmare. A nightmare.
Okay.
I'm joking,
Thank you
of
very
course.
much, Simona. Thank you.
Thanks to you.
Are there other questions? I actually have a curiosity, Simona. It's about actually the last slide that you showed about team soup condition. So up to now, for like this kind of high mode resolution, solution, let's say, there is no idea about the IMSUP condition, if it's verified or not, or there are some hints.
There is a thumb rule which works.
Okay.
In the publication available so far, which leads us to essentially preserve the standard choice for the finite element discretization concerning the discretization adopted along the mainstream. While the lacking information is what about the number of modes, and the thumb rule seems to be select 2 modes, 2 additional modes for the velocity with respect to the number of modes required for the pressure. Okay. So for instance,
yes, maybe also in another slide it was exactly
yeah,
modes.
wait, it was before. It was but with Thomas, we are working also on that, and so this is what we have done before starting to work from a theoretical viewpoint. Okay, so the standard mismatch +1 in terms of finite element discretization, cubic, quadratic, 2 additional modes for a velocity with respect to the number of modes selected for the pressure. Okay, but from the investigation we are carry out together with Thomas, actually it seems that the geometry plays a role. So if your geometry is more regular, probably this mismatch is not necessarily demanded. Okay, while if your geometry becomes more complex, probably you have to move to this rule.
Okay.
So it is something we are still working on. But the numerical evidence goes in such a direction, at least for configurations which are complex from a geometrical viewpoint.
Okay, great. Thank you very much.
You're welcome.
Are there other questions? It seems to be not the case, so I think that we can thank again Simona, and
Thanks
we
to you again. Sorry for the mobile ring.
Don't
Terrible.
worry, it's fine. Don't worry.
Okay, sorry.
And we see
Bye,
each other next Tuesday. Bye.
See you.
Ciao.
Bye-bye. Thanks again.
Ciao,
Have a
ciao.
nice afternoon.